This is a supplemental video for one of the CS202 sections. This section has had two holidays, so we didn't necessarily get a chance to cover all of the material that's relevant for assignment 4. So I'm doing this just to cover some of these topics. We will also talk about these in class once we are done with the exam. But I just want to get these out of here if you want a more detailed explanation than what's available in the assignment video. So in this video, I think we're going to focus mostly on implementing one data structure that will be relevant to the assignment, and then just talking about some relevant terms that might help you. So what I want to do first is define a few problems. So first, we're always given a real world problem, and then we have to figure out how to program it, right? Or come up with a algorithm first, and then implement that algorithm in one of our programming languages. And so you might come across several examples in the real world that require different data structures, or would benefit from different data structures. So, for example, let's say you were given a fantasy baseball team, or even just like a baseball team where you need to keep track of the lineup, who's batting first, second, third, etc. What we could do, right, is maybe create a struct for the player, which we'll assume we have already done, and then I know that a baseball team, for example, always has 9 players, or 10 players if it's the American League, Major League Baseball. But let's just say 9, right? You have the 9 positions. What we might do then is create an array like this, where we say players, and then there's exactly 9. This is how we approach things in CS 135 with a data structure called a static array. And the thing about a static array was that it always gave us exactly as many spaces as we told it to give us. So if I ask for 9 spaces, I'm going to get 9, and there's no way I can get any less or any more. This is appropriate for something like a baseball team because I know in advance there are going to be 9 players, and this isn't really going to change unless the rules of baseball fundamentally change. So I don't really need any more than 9 or any less than 9. The problem with this, though, is that if we encounter a scenario where we don't know how many things we are going to need in advance, like for example, if we wanted to read in how many items are in our game, like we're doing an assignment for. So if you are programming a video game and the number of items is maybe known by the designer but changes over time, so maybe you get 10 items at launch and then 15 items when you add DLC, and then 20 items 2 years later when you add more items to the game, then we're not going to always have a same fixed amount. And so if I just arbitrarily made an array with like 100 items in it, like this, and this was slot 99, and this was slot 0, then I'm limiting myself to only 100 items. If we run out of space, if we do a lot of expansions to our game and we eventually hit our 101st item, it's not going to be able to store it in this array. And in the time that we are building up to those 100 items, maybe if we start with 10 and then 15 and then 20, there's going to be wasted space, right? Like if I only have 5 items, then I'll fill these 5 slots, but the remaining 95 are all completely empty, which means that I have 95 memory blocks that are completely not in use, and I could be using them for other things, right? So it's kind of a waste. Okay. So this might be nice. I think we did get a chance to cover dynamic arrays. So the new keyword works with both arrays and objects. And if I could figure out a size based on, like, get the size from a database, right? We're on update 4.2.3, and the size of how many items I have is now 15. I can get this information from somewhere, right? For the sake of our discussion, I'm just going to read it from CN. But the reason why we would need this is that it's non-constant. I don't know exactly how many I need in advance. And so if I want to allocate this now, I can use the new keyword. And what this will do is it will create this array only when we get to this line, whereas when we do this one, it creates it automatically. So this guy would be our dynamic array. It's an array that we create while the program is running that can have any size that we can figure out while the program is running rather than just give it a strict constant. So we talked about how this addresses that weakness of static arrays and that we don't need to necessarily waste space if we can at least ask somebody how many things they want, right? Adding another layer to this, sometimes we can't even ask somebody how many things they want in advance. Maybe that just detracts from the user experience or is difficult because maybe they don't even know, right? The user we're getting things from doesn't know, or we're receiving things from different sources and that information is hard to get. So the example I like to give for this is you go to a drive-through and you want to implement a system that keeps track of all the items that somebody is ordering. Right? What food items from the menu are they ordering? This is another case where we can't know an exact size in advance, right? You can't just ask somebody, how many food would you like? And like expect them to answer, be like, yes, I'd like 5 things, a hamburger, a cheeseburger, a shake, right? That's a weird question to ask them. And at that, like they don't even necessarily know, right? So it's going to change between people. It can't be a static array. We're not always going to have the same amount. So it might be in our best interest not to do a static array. And we can't get the amount from the user directly because they might not know. They might even change their mind, right? Like somebody might go up to the drive-thru and get a cheeseburger, a shake, fries, 2 drinks, and a apple pie, and then they change their mind and remove some of those things because they realize it's too much or something, right? They stop themselves. So what we need is a different data structure that is maybe more capable of handling a flexible scenario like that, where we receive data in an online fashion. That is, we get the data over the course of the program, and your solution to this might be a vector, right? So you might say, well, that seems like a use case for a vector. So maybe if I have a vector full of food, and I call this the person's order. And then what I can do is I can hook up each button on their thing so that when they click the hamburger button, it pushes a hamburger into the vector, in which case we only have one slot where the hamburger goes. And there's no other space allocated. So it's not going to be wasting any space. And this allows us to not be married to a size either, right? So I don't have to ask you, how many things are you going to order? I can just make the array bigger every time they click a button by adding something into the vector. So if they now add a shake, then we can create one more slot here and put the shake in that, right? So if you arrived at a vector, I think that's completely fair. And so what I want to do today is actually talk about how we could implement a vector. I may not do this like the actual vector is implemented in C++, but I want to at least come up with something that's similar in that it's going to allocate as many spaces as we need. So it'll only add a space whenever you add something to the actual data structure. And so it will only have as many spaces as there are things. Right, so let's actually get into the code. I've at least come up with some declarations for our class here. For the sake of simplicity, I'm going to make this hold integers. So I have 2 members. I have the array containing whatever our items are in our list. I've hard-coded this because unlike a vector, the angle brackets stuff we haven't necessarily gotten to and how to like change the type that it holds. So for now, I'm just going to do it as an integer. The second variable I have is a size, which is just how big the array currently is. And then you'll notice that I have 4 other functions here. I have one that adds an item to the back. This is akin to the pushback that you may have seen in a vector. I have one that prints it just so we can make sure that it actually is working, and also to get a handle with using dynamically allocated arrays, a constructor and a destructor. Now I've written the constructor in advance. What this will do is it will just simply create an empty list, and it will do this by setting the array equal to null pointer and the size equal to 0. So what we may have noticed in my example that I drew out here, right, is whenever I do a dynamically allocated array, the new keyword always gives me a pointer, and so my arrays, if they are dynamically allocated, need to be done with pointers as well. Okay, so I'm doing this to be a one-dimensional array. And because it's a pointer, if it's not currently pointing to anything, I actually don't want any allocation if there's nothing in my array. I can't really allocate an array of 0 things. I think it will allow you to do that, but maybe it doesn't make a whole lot of sense. So just to avoid allocation, I'm going to set this equal to null pointer, which if you remember is just a value representing pointing to nothing in particular. I set the size equal to 0 since there will not be nothing in the list when we first construct it. Afterwards, let's actually do these functions now, and hopefully we understand that when we start out with the list, the array will be null pointer and the size will be 0. Okay. So what I wanted to do is implement these 3 functions, and then also take a moment to talk about destructors now in relation to our dynamically allocated memory. Okay. So really quick, let's now work out how we are going to implement this behavior where it gets bigger by 1 every single time. The way I like to do this, if I have to design something for the first time and nobody's given me a solution, is that I like to draw out a picture. And what I want to identify is what the states of the thing I'm working with will be before and after my function is done. This is a common programming strategy, is just think about what you want all your variables to be before the function is executed and after the function is done. And so if I think about my add item function, I might come up with a before situation where, okay, here's my array. It contains, let's just say 3 things in it. It contains 4, 7, and 9. And I know that my variable r needs to be pointing at that array because it's the pointer to the array that we're currently using for the list. And then my size is going to be 3, right? So the size tells me how big the array is. And then after I'm done, there's some steps in the middle. My function does something between here and here. And after I am done, what I want to happen is the array should be bigger and then contain whatever I want to add to it, right? So if I'm adding like add item, the number 2, then we should go from this to that, right? We should start with this first part, and then by the time we're done, the array should now be a bigger array, and the size should maybe go up by 1. And the way I identified that I needed the array and the size is that you should consider what variables you'll have access to in the function that you're writing. So there's 3 variables here that I have access to: the array, the size, and then actually the item that we are adding to the array. So I need to consider what those 3 things are being used for. And if I look in my code, the way you should identify what you need to do your work with is you should look at the inputs that you think are necessary. So here my function takes the new item, and then consider that when you're writing a class, you will always have access to the class members as well. So it doesn't really matter about the modifier. Since I'm in the class, I can access private, public, and protected. And so what I have access to is these other functions if I think they're useful. But if I'm thinking about variables, I have access to these 2 things, the array pointer and the size. So I should probably think about, do these things need to be modified between when the add item function starts and ends? And it seems like both of them do, right? Because the array should get bigger and the size should go up by 1. So think about what variables you have access to, and then maybe prune down to the ones that you think are relevant to your function and which ones need modified. Okay, so now we have a goal in mind. We are given this array, this size, and this number that we want to add. And when we're done, the array should be bigger, the number should be in the array, and the size should be bigger. So let's start with what we have. We have 4, 7, and 9. And what we need, what we need when we're done is for this workspace to end up looking like the after image. So let's start thinking out some lines of code. Well, one thing we might notice is that we definitely need that bigger array. So it doesn't exist yet. We only have the array of 3, which means I need to make a bigger array. Okay, well that's easy enough in my code. I can simply add a line that creates an array where the size is 1 bigger, right? Now I'm not actually storing it anywhere. I need a pointer on the left-hand side to hold this array, otherwise it's going to get allocated, and then we'll just lose track of it and memory leak it. So if I look here, well, this bigger array is definitely what array is supposed to point to by the end of the function, right? So maybe I could simply take this R pointer and have it point to this array. If I do that in my code, I can simply say R equals new int size plus 1. But the difficulty is now this array that R used to be pointing to has no pointers to it. If you remember, that's the definition of a memory leak, meaning that there is no way for me to go back and access this information anymore. It's going to sit there, be allocated in the program, and be unusable to anybody, which means I've now wasted 3 spaces, and if I continue to do additions, I will have left every single array that came before this one. So I will very quickly run out of space. So I can't actually use this R pointer to point to it, which means I need to maybe deallocate this guy first before I do that. And so if I deallocate this, if I do delete R, and if you remember when we're deleting arrays, we need to use the braces, so I need to do that. Then this is okay. I've at least gotten to a point where I've gotten rid of this information and can maybe now safely update it to this. But the problem is that our new bigger array is bigger, but it needed to contain the 4, 7, and 9, and I just threw that out by deleting it. So as we'll find here, there is no way that I can use this array pointer to immediately point to the new big one. That's not going to work out for me because I'm either going to lose this information up here, memory leak it, or I'm going to deallocate it while it still has numbers in it that I need. And so what we'll do is let's just create a variable local to the function, just for the sake of copying over our data, just for the sake of keeping track of this array while we're still working. So what I'm going to do is I'm going to create a variable. I'm just going to call it temp. And we'll note that I can't delete this array right off the bat because then I'll lose that information and can't copy it over. Now we've allocated that bigger array. We can now copy over the data. There's a more efficient way to do this, but I'm just going to do it with the for loop. And what we'll do is the new array will contain the elements from the old array. And so what I'll get here is I can now copy this data over, copy the 4, the 7, and the 9 using a for loop. And I am now safe to throw away this old array, this small one, because I've gotten the information out of it. It's no longer needed. So we can now deallocate this. And we're getting very close. So we now notice that the array is pointing to that old location, which is a dangling reference. We maybe want to fix that by making it point somewhere else. So I'm going to make it point to this same array that temp is pointing to. It should be pointing to the big array by the end, right, as we noticed on the right-hand side. So I can do that pretty easily with pointers. I can simply set r equal to temp. And then there's two last things I need to do. The first thing I notice is that my size is still off. It's 3 here, but it should be 4 when we're done. And it should maybe reflect that here because now the array is pointing to an array of one bigger size. So maybe we'll do size plus plus. And then finally, the last thing that we're missing from this picture on the right, and what we currently have, is that the 2 needs to be placed at the end. The 2 being the new item that we're adding, and then that should go at the location of the size before incrementing it, right? So if the size is currently 3, then this would be index 0, 1, 2, and 3. So the size will always be where it should go if we just resize the array. So I'll use the size for that, and then increment it afterwards. So we'll make this equal to 4 now. And you'll notice we started with the thing on the left, and we've now arrived at a situation that is essentially just the right with this temp pointer added. But since I've made it local to the function, when the function ends, it will disappear. So it will just go away. Now there is one last thing I should consider, which is that this array could be null pointer, because when I allocate it here, it's totally possible that the constructor allocated it, or did not allocate it. It didn't create any actual array, it just set equal to null pointer. So anytime I use the array, I should maybe make sure that it's not possible for it to be accessed if it is null pointer. So if I look at my 2 lines where it actually gets used in the expression, so if places where it's used in a get context rather than a set context, that would be right here and right here. And then here it's set to an array, and here it will have been set by this line. So there's no possible way that it could be null pointer. So I should look at these 2 lines. If we look at this line, this is in the for loop. It will execute when I is less than size. The middle condition will execute what happens here. And if the size is 0, like it is when we actually allocate this list, when we call the constructor, then this will be equal to 0, and 0 is not less than 0. So this actually gets skipped in the case that it's null pointer. That seems to be okay. This guy, on the other hand, has no condition around it. There's no like if statement or for statement. It will just always execute. To be safe, we should maybe then add this to make sure that the array does not equal null pointer. And only deallocate it if it is not null pointer. If it is null pointer, then that means that we have not allocated it. That means there's nothing for us to delete, and we can't get away with that. So we'll simply just make sure that it exists before deleting it. Finally, this should be correct now. So we're going to make the array bigger, copy over the information, delete the old array so that it doesn't memory leak, make a copy, and then put the thing in there. Now I want to point out that there are 2 different types of copies happening here, and I just want to define them so that we have the terms. The first kind of copy that we make is a shallow copy, which is when we have 2 pointers to exactly the same data. This happened when we had our R and our temp pointing to exactly the same information. This line right here is an example of a shallow copy. So this is considered a copy in that R and temp are both pointing to exactly the same information. And so it's kind of like I have a copy of it, and then I'm setting something equal to the other thing. This will occur when we copy things that are of reference type. So I'm copying a pointer to a pointer. They're now pointing to the same information. So this is called a shallow copy. It is fast in that I just have the data that I want both of these to point to, but there's not really a true copy there. It's just they're kind of 2 names for exactly the same data. That means if I modify one of these, it will modify the other. which is maybe not what we always want, right? The other kind of copy is called a deep copy. A deep copy is when we have two actual copies that are the same data, but get two separate memory allocations. This also applied to R and temp at some point in time, where if this contains some numbers, and this contains the same numbers, these are copies of one another. They're basically clones, and the information in one of these will not be modified if I modify the other one. So if I do like R sub 2 equals 3, it will modify this 7 to be 3, but it doesn't change the temp, right? It stays exactly the same. And this is how things work when we do like int x equals y in C++, is it makes a deep copy of the information. This is needed when we don't want the data to be shared. We don't want to modify one and have it modify the other. And we should note that it is slower than a shallow copy. So the shallow copy is as easy as just making these two things point to one another, but the deep copy can be slow and requires double the amount of memory because I have to have two actual copies of all of the information. I do a deep copy in my for loop here because I am taking this information and copying over all the elements one by one. Finally, let's just finish up the print function and the list destructor. The print function, I just want to make sure we print all the elements in the array. If you were to print all the elements in the array without the context of this whole lecture, you would just write a for loop, right, and then see out the actual elements. So I would see out our array sub I, and then maybe not an end line, maybe an end line at the very end. And what you'll notice is that there's no real difference between the way that we print things out when the array is dynamically allocated with this pointer and the way that we use it when we have a statically allocated one. It's just use the indexing operator, these square braces. It will work totally fine. You don't have to do anything special. After you have the allocation out of the way, nothing different about the way we use this array. Finally, we have a list destructor. The destructor, if you remember, gets called whenever something is deleted. This happens when a variable goes out of scope of a function, or just out of scope of, like an if statement, or a for statement, or a while statement, or an arbitrary scope. And it also happens when we delete something. So if I did delete and then the list, it will also call the destructor. So remember, it's like the end of the life of that object. When that object's life ends, it will call the destructor. We didn't really have a reason to use this previously, but now that we have dynamically allocated memory, I think there's actually a reason to use this. So let me do a quick example here. So let's do two examples. Let's first start with a simple struct that has a name and an age. So if I dynamically allocate something of this struct type, if I say person pointer p equals new person, and then I use this, so I start actually setting the name, setting the age, I do something with the code here. We know what this does is it makes a p that's equal to the address of this guy. And so we get this object at address AC that has a name and an age within it. I've been drawing these as bubbles, and that's because the information is contained within that object. The name and the age, if you remember, are non-static, and so they're contained within that object. There's an ownership to them where they actually belong to it. When I do something like this and do delete p, or if it goes out of scope, if I did a non-pointer and it just was the end of the function, this would happen too. What the compiler is going to do is it's going to say, okay, I'm going to go to this location AC that the P that you are asking me to delete is at, and I'm just going to erase the bubble. So I'm going to get rid of that information. It goes away. In this situation where we just have a person pointer or a person class, it's okay for this to happen. This is totally fine. So all the data that we were using, the name and the age, went away. We won't have a memory leak. It just works totally fine. However, if I was to use our list class, so let's say I do a list here, and then I add something to it. So I do list.addItem 4, and then list.addItem 7. And then I finally delete the list at the end, or it goes out of scope. Note that if it goes out of scope, it will delete the pointer, but not delete the object being pointed at if you use a pointer type. If you don't use a pointer type, it will delete the object directly. The compiler will. But what this does, right, is we get a list. It points to some address. Oops. And here's our object down here, right? So it's at address 1, 2. What our list contains is it contains an array and it contains a size. And in our scenario, this size is a 2, and the array is going to be a reference. So it'll be something like 1A that points to information that is just somewhere out in memory, but doesn't necessarily belong to this object itself. Because of that, if we ask it to delete the list on this line of code, what's going to happen is it's going to simply, like it did with the person, destroy the object at address 1, 2. So it'll kill this guy, this bubble, and everything in it, including the pointer to the array and the size. But notice it didn't do anything to the array itself, because all it's going to deallocate is the things that belong to the list, which is the pointer to the array and the size. So it destroys the pointer, but not the guy being pointed at, because that's not actually inside the bubble. It doesn't belong to it. It's more like, please go make this and just tell me where you put it, and I'll write down where you put it, right? So it's almost like, if I gave 3 students my email address and one of them lost it, then the other people might still have my email address and I still exist. So I'm not like in what's being lost by that person, right? It's still just kind of like a reference, a pointer. It tells you where to find it. Because of that, when we have dynamically allocated memory, where we've used the new keyword to put something outside of the bubble, it's going to require us to write a destructor in order to avoid a memory leak. The memory leak occurs because it's automatically going to erase all the information, and we know that the point of the destructor is that it gets called as the object is being deleted. The destructor has no parameters, as we discussed when we started out. And this is because it automatically gets called when things go out of scope or when you use the delete keyword, and we're just going to simply use it to clear up any dynamically allocated space before the bubble is totally gone. So this occurs before the bubble gets erased. This will get called. And in my scenario, what I needed to do is delete that array we saw, right? This array is still left over. So what I need to happen is this guy needs to go away. And then once that's gone, it is now safe for me to erase the whole bubble, because there's no more things that are outside of the bubble that I could lose. So actually for this, I'm just going to actually copy our exact same data here. The other thing I need to deallocate is the array itself, and then I need to make sure that it's not null pointer on the off chance that we call the constructor, don't do anything with the list and destruct it, just to be careful. This now should be okay. So we have this code to create things in the list, to print, and then to destruct. I can then use these in my main, so let's just see it in action really quick. We could see list.addItem, or list.addItem 7, maybe print the contents of this so that we can make sure that it's working. And then maybe add some more things to it, right? Add item 5, add item 9, and then print that out again. And just to see in action that the destructor works, let's just say cout destructor. So when this function is called for the destructor, we'll see that it gets printed. And if I run this, we get this window here, and we'll see that it first prints the 4 and the 7 for this part up here. We add the 4 and 7 and then print the contents. Then we see 5 and 9 get added to that same list. So we now have the 4, 7, 5, and 9. And then only when that's done, when it gets to this line of code down here that ends main, does the destructor get called for the list. So the list will, in this case, go out of scope, and so that's when it gets destructed. Just to show that it also works with our pointers, let me change this list from a normal object to a pointer. And then I can replace all of my dots with arrows because we maybe said that those are equivalent just for pointers. Oh, whoops, it also replaced my dot in my list.h. And then finally, so actually just to show it, if I do not put the delete keyword, this will memory leak. It's not going to explicitly deallocate the list, just to show that. So notice it does 4, 7 and 4, 7, 5, 9. But now it does not go out of scope. The list doesn't, at least. Its pointer goes out of scope, but not the list itself. So when I have something that's being pointed to, I need to explicitly delete it with the delete keyword. And if I rerun this now, we will see again that the delete keyword is now what calls the destructor. That about does it for everything I wanted to cover relevant to the assignment. So I encourage you to check out the video as well if you haven't. For that, I should timestamp that soon. That way you can maybe click around in that video too. But these are just some things that I thought were relevant that I wanted to cover since we are having some trouble with the holidays.